So we're going to be doing Chapter 9 this morning. In Chapter 9 for CCENT, we'll be covering network address translation. This is a little bit of a relaxing chapter, if you will, because the concepts that we'll be talking about in this chapter are not nearly as in-depth as what we've been seeing over the last few chapters. But I promise you this is only a slight reprieve as we get into much more detailed discussions as we move forward. As you guys know from our discussions yesterday, IP address space is not big enough to allow us connectivity for all of the devices that we're connecting to the network, right? Private addressing, we talked about that yesterday, that RFC 1918 address space is designed to help our organizations deploy IP addressing internally without having to have public domain or publicly accessible IP addresses. But the problem with private addressing is they have to be translated before you can go out to the internet, right? That is by rule. RFC 1918 addresses are not routed by service providers. So it's a good thing and a bad thing, right? The good thing is that we can use this addressing internally however we like, and we can allocate addresses to whichever devices we like in whatever format we like. But as always, there's a need to translate those addresses as we go to the internet. Traditionally, that's caused some problems, right? Certain applications, certain functions that we perform in the network don't usually work very well with this type of translation process taking place. So we try to get away from that in IPv6. This chapter focuses primarily on IPv4 because, as you learned yesterday, IPv6 doesn't really have, as a mainstream option, doesn't really have network address translation built into it. Again, it's not to say that there isn't a private addressing definition in IPv6. However, that private addressing definition has been deprecated, and most people that choose to implement IPv6 simply don't use that specification. Just a quick review of what we talked about yesterday, the RFC 1918 address space. That is our Class A, Class B, and Class C reserved address space. The entire 10 subnet in the Class A range is private, which means that you can use that in any way you wish as long as you translate that before you go to the internet. Now, in the Class B range, we use a subset of addresses. We don't use an entire block, a block that falls within a major network boundary, I should say. We use 172.16 to 172.31. In the Class C space, we're using the entire 192.168 range for our private addressing. There's a bit of a typo there. There's an octet missing. But it is the entire 192.168 range of addresses that we use. So this concept of network address translation is to take our private address range and at some boundary, usually a device that's connected to the internet, we do a translation to some public address space. There are three ways to do this translation. You have static NAT translation, where you're doing a one-to-one type of NAT. You have dynamic NAT, where you're using a pool of addresses, and you're translating to a pool of addresses. And then we also have something called port address translation, or overload. And overload, we translate any number of addresses internally to a single address on the internet. Okay? So we'll talk about all those different types of NAT as we go through this process here. The other thing to keep in mind is that this device, whether it's a router or a firewall or maybe a little wireless access point that has some routing functions on it that you might connect to your home internet connection, regardless of what type of device it is, that device maintains a database of these translations. All right, so as translations occur, We update that database with information about those translations so that when traffic returns from the internet, we reference that database so that we can do our reverse translation or translate the addresses back into the opposite direction. What is NAT? Well, like I just said, NAT is the purpose or the process to translate private addresses to some sort of globally routable address. By the way, it doesn't have to be private to public. In some instances, you will translate public to public. In some instances, you might even do something called twice NAT, where you're not only natting the destination, or they're not only natting the source address, but you're also natting the destination address. All right, we're going to focus primarily on the basic concepts of NAT in this class. We are going to look at some configurations, and we're going to look at some various options for configuring NAT. Our focus is going to be on implementing NAT on a Cisco router, though. I want to make that clear because in an ASA firewall or other network devices, the concepts are the same, but the implementation process is different, right? For example, on an ASA, an adaptive security appliance, which is a Cisco firewall, you have policy-based NAT that you can implement. You have object-based NAT that you can implement, and so on. All right? NAT, of course, is going to be implemented on your border device, the device that has an attachment to the internet, as well as an attachment to the inside of your network. In a lot of cases, that device has some sort of private addressing internally and then public addressing on the outside interfaces. All right, and we'll look at that as we look at some examples a little bit later on. So here's a topology where we have an internal private address space on our internal network. We've got some 10 addresses, we've got some 192.168 addresses, but those are all RFC 1918 addresses. We've got a router that connects to the internet. On the outside of that interface, or on the outside of that router, we have a public IP address, and of course on the inside of that router, we have our private address. Okay, so that is our NAT-enabled router. One of the things that you're going to have to know for the exam, and as well as just in general, if you're working with NAT, there are some terms that people get confused about when they're dealing with NAT in general. Okay, so I want to define these terms because it's very important that you know them. It's all about the perspective of the host and the location of the address. Very, very key here. All right? And you may have seen, if you've dealt with NAT in the past, you may have seen these terms in the past before. Inside local, inside global, outside local, and outside global. First thing to understand, inside. Let's talk about that first. Inside is the originating host. Well, if the traffic is coming from inside your network. Inside does not mean private. Inside simply means the source of the traffic. We're assuming we're not initiating the connection from the internet. I'm talking about this private address space. Every one of these hosts in this network here are considered inside. The device that I'm communicating to on the internet is considered to be my outside device. Okay? Even if the connection is coming from the outside and traveling into the network, maybe somebody is trying to access a web server or an FTP server inside your network, the terms still apply. Outside is the host that you don't have control over, you don't have configuration management control over. Inside are your internal hosts. But do not confuse the term outside with public or inside with private. That's not what it means. Inside simply means the host that's inside your network. Outside means the host that's outside the network. Local and global, this is the perspective. Local means private. Global means public. Okay? Another way of considering it, and we use these terms for the ASA, local means real, global means translated. okay? At least from the perspective of the inside host. So when I say, what is your inside local address? What I mean to say is, what is the real address of your inside host? Or in this case, what is the private address of your inside host? If I say inside global, what is the translated address of your inside host? What is the translated address of your inside host? Or what is the NAT address or the public address of the inside host? So global generally means public and local means private. Inside means your inside host. Now, as far as the terms go with regard to the host on the outside, outside local and outside global, almost always these addresses are going to be the same in some sort of translation scenario. And here's the reason why. It's not that they actually are the same. It's that the private address of your destination is very rarely actually known. So in our translation database, outside local and outside global are often referenced as the same value, the public address of the destination host. I mean, technically, outside local technically means the real address of the destination. But you very rarely know what the real address of the destination is because it's hidden. Now, you may know in some scenarios where you're connecting to an extranet or a private network, but as far as it goes with devices on the internet, outside global is what you know. Outside meaning the host that I'm talking to outside of my network, global meaning the real address. Excuse me, the public address. Yes, sir.
So we can say that the inside global, it's not in my network, but between my router and my ISP, the internet provider.
Yes, the inside global address is not inside your network. It is the public address that you use to translate your inside local address. And yes, it would be on the outside of your network. Now, how that address manifests itself, in other words, how we actually define that address, can be done in different ways. And we'll see that as we progress through the rest of the chapter here. Okay? You guys have been reviewing your questions. You probably saw maybe some references to these terms in the review questions, right? NAT used to be covered heavily on the second test. Now it's been moved primarily to the first test, okay? So how does NAT work? Well, it's very simple. You have a device that is attached to both the internet and your inside network, and on that device you define your NAT policy. That NAT policy identifies the source of the traffic, and it identifies how that source traffic is represented on the internet. In other words, how does it get translated? And then on top of that, it identifies which interfaces are participating in this translation process. We'll see this when we start to go through the configuration. We actually define what the interfaces are that are participating in this translation process. And then lastly, it maintains a database called a NAT translation table. In a firewall, it's called an XLate table, but a NAT translation table that allows us to identify active translations. These translations have to be monitored and maintained because we're trying to match a flow of traffic in both directions. Very, very important. All right? So inside local, now you know if I say inside local, I mean the real address or the private address. Destination address. It says outside local, but notice that address happens to be the same as outside global. Like I said, outside local is almost always assumed to be whatever the outside global address is. So it's just a host on the inside of your network going to a web server, for example. Inside local gets translated to inside global. Inside local gets translated to inside global. So the 192.168.10.10 address gets translated to 209.165.200.225. On the reverse side, traffic flowing back in, okay, the router, and actually I should have mentioned this before, the router has a configuration on the interfaces to let the router know these interfaces are participating in NAT. So when traffic hits this outside interface, because the router knows it's participating in NAT, it references its translation database and looks to match things like the source address and the destination address. Those two addresses match an entry in the table, so the translation takes place and the source address stays the same, of course. The destination address becomes inside local. All right? And this happens in real time, dynamically.
In the two situations, it looks like the outside and the local or global, it never changes, still the same.
That's right. In both situations, outside local and outside global are the same, because technically, what does outside local represent? If you follow the terms to their definition, outside local means the real address of your destination. Now, it may be that that real address is the public IP, but in most cases, that's not going to be the case. Right? If you're going to the thinQtank web server, for example, we're hosted in a data center in Europe, 1&1, and we have a real public IP address on our server. But if you were, say, accessing a web server at this company's location, most likely that web server has a private address. And all they're doing is translating that public IP to that private address. But that private address is never known by you. It's hidden. So for that reason, outside local and outside global almost always look the same. So we're going to look at different types of NAT as we progress. Like I said, there are 3 types of NAT that are available: static NAT, dynamic NAT, and overload, or what we call port address translation. Static NAT is a one-to-one mapping. So the whole point of static NAT is not to preserve address space. But there's a very special use case for static NAT. It allows us to allow hosts on the internet to initiate a connection without having to have that connection initiated from the inside of the network first. All right, we have a comment online. It is difficult. It's different for our personal homes versus college. The college has real IP addresses, so when traffic goes outside the network, it's translated to their router. But at the home, I do not have my own IP address. Actually, you would be surprised. It's actually pretty much the same. You go to a hotel, you go to a business, you go to a college, you go to your house, almost everybody runs the exact same type of NAT, overload, okay? Even colleges themselves will have private addressing internally. It's very rare that you'll actually even see public IPv4 addressing in a large campus anymore because the addresses just aren't available. Now, you may have some legacy installations where colleges, because colleges were actually some of the first organizations to get large blocks of addresses where they would have public IPs. And they may even still want to translate those to a different IP to protect themselves, right? But essentially, and you guys will understand this as we finish up this chapter, everybody kind of does the same thing, all right? The NAT translation that we're performing is something called port address translation, all right? And I'll actually go into that in more depth as we progress through the chapter. I want to make sure that you guys understand that concept of port address translation before we actually start getting into the discussion of its application. But I will say this, just to answer the question that we were posed online, 99% of the NAT that exists today, regardless of where you are in the world, in IPv4 is done the same way. It's done with port address translation. In other words, everybody's getting translated to the same IP. Okay? Now with Static NAT, that's not the case. In Static NAT, we have mappings of 1-to-1. So for every inside local address, we have a single inside global address. You might think about that and go, well, that's great, but that doesn't really help me with preserving address space. Well, that's not really the point. If you have servers that are hosted inside your network, and you want clients on the internet to be able to access those servers, then you need a static NAT scenario, because the translations, static NAT translations, are permanent. They can be used for either inbound or outbound traffic flows. So static NAT translations always exist in the table, in the database, and they're permanent. All right, so for example, if a customer has a publicly facing web server that they want their clients to be able to access, to look up company information or whatever it might be, that server might be hosted inside their network, and it might actually have a private address. And that server can go out to the internet just fine because it can translate using a dynamic process. But the dynamic process doesn't allow people to connect to that server unless the connection's already been established from the inside to the outside. So what do? We set up a static NAT translation that allows that communication in both directions. All right? We'll see a kind of a visual representation of this here. So here is a PC on the internet. That PC is got this address, 209.165.200.226. You've got a server inside your network. Now, for whatever reason, I've decided that I want to allow SSH to that server. Maybe somebody is working from home and they need to access that server so that they can do some configurations or whatever it might be. Okay? Well, you're not going to be able to SSH to the 10.10 address because that 10.10 address is private. It's not routable on the internet. So on our router here, we would set up a policy that says, okay, let's go ahead and establish that the 209.165.200.226 address always gets translated to 10.10. So when the person on the internet wants to connect to that server, they don't use the 192.168.10.10 address. They use the 209.165.200.226 address. Yes, sir.
So by reserving the 209.165.200.226, that never changes.
That never changes for that server. That's correct. Hence the term static, right?
Yes.
Static means permanent. Okay. In addition, this would be the same translation that would be used if the server was going out to the internet. All right. Now, this is not a common form of NAT, at least not for your dynamic hosts, but it's very common for your web servers, your FTP servers, anything that somebody needs to be able to gain access to from the outside. We do the same thing in an ASA. In a firewall, we set up access rules and we set up static translations to allow people to gain access to specific resources. All right. We have a question here. Would radius servers use static NAT? It actually depends. All right. If your radius server's on the inside of the network, but the device that's performing the authentication is on the internet, then no, because the communication goes from the device on the internet to the radius server. Right? And whenever you have any kind of extensible authentication like that, where you're sending authentication back to a server, the client is not communicating directly with that server. The client is communicating with the device that they're connecting to, okay? Which could be a firewall if it's VPN, or it could be a router or whatever. But to further answer that question, I'm going to say, look, it doesn't matter what kind of server it is. It could be a radius server. It could be your home computer. It could be a time clock server. If you need to access that server from the internet, and that server's inside your network, then the static NAT rule would apply, regardless of the protocol, regardless of the application. None of that matters. So yes and no to answer that question. Could be that you would need a static NAT for that radius server, maybe not, right? And like I said, it depends. And you can even extend this NAT concept. We don't get into this in this this course, but you can even extend this NAT concept to where you're doing things like port forwarding, where somebody's accessing a public IP address on a specific port, and you have a policy in place that says, if somebody tries to connect to this address on port A, send it to this server. But if somebody tries to access this IP address on port B, send it to a different server. That's more of a policy-based NAT environment. Okay? And we're going to see the configuration of these in the rest of the chapter. We're going to be going through a lot of examples here. We're not going to do a lab in this section here. We got plenty of other labs that we'll be doing, but not for NAT. All right? Dynamic NAT, probably the least commonly used form of NAT. Dynamic NAT. When you see the word dynamic in relation to NAT, always think pool. Always think pool. These are synonymous terms. A pool meaning not a swimming pool, not billiards. I'm talking about a pool of addresses. So if somebody wants to go to the internet, they're not using the outside interface of the device to get to the internet. They're not using static NAT to get to the internet. They're pulling an address from a pool of pre-configured public addresses. All right? It'll make more sense when we look at a visual representation of this on the next slide. All right? The problem with dynamic NAT is that the pool has to be as large as there are the number of hosts going to the internet. If you have 100 hosts going to the internet at the same time, then you need 100 addresses in the pool. If you only have 10 addresses in the pool, then only 10 hosts can go to the internet at one time. Okay? The analogy I like to use, it's common, we see this a lot in a lot of buildings here, where you have kind of a shared, like an office complex where you have multiple offices on a floor or multiple companies on a floor, but the bathrooms are in the hallway. And what do you have? You have keys to be able to access the bathroom. Well, maybe you have 3 keys or 4 keys to go to the bathroom, right? That's your pool. When somebody wants to go to the bathroom, the restroom, the water closet, whatever you want to call it, they grab a key from the wall, they go use the restroom, they come back, they put the key back on the wall. Well, same kind of concept with a pool of addresses. You want to go to the internet, you grab an address from the pool. When you're done going to the internet, which sounds really stupid because nobody's ever really done going to the internet, you put the address back into the pool. Okay? Believe it or not, there was a time when hosts didn't have to go to the internet. You would only go to the internet for certain things, right? Now that's not so much the case. We go to the internet, well, all the time, right? All the time. So here's a visual representation of that. I have a pool that has been configured on my translation router. That pool has these addresses in it: 226, 227, 228, 229, 230. Each time a host goes out to the internet, they snag an address from the pool, they use that address while they're active on the internet. When they're done going to the internet, the address goes back into the pool. You can see why this is the least common form of NAT. It's not really that practical. But I will say this. In combination with the next type of NAT we're going to see, this NAT is used quite a bit. All right? That doesn't make any sense right now, but it will make sense in a little bit. The last type of NAT we have is something called port address translation. This is the most common form of NAT, regardless of the vendor, regardless of the equipment, regardless of the type of connection. Your home, a hotel, most businesses, getting internet on an airplane, it's all the same. We use this port address translation. Essentially what port address translation is where you take any number of hosts on the inside of the network and you translate them to one single address. Let's see what we got here. What type of NAT is used in real life? Is it PAT? Yes, it is. Absolutely. It is this form of network translation. And it's complicated. There's a lot of things that happen with port address translation to make it work. Because if you think about the concept, you might have 1,000 hosts inside the network, but when they go to the internet, they all look exactly the same. They all have this same IP address. If all of our computers, if we opened up our computers and went to IP Chicken right now, we would see that we're using all the same public address. Okay? So what's the challenge? The challenge is to make sure that the return traffic goes to the appropriate host, right? Okay? So what we do for that is we maintain a detailed database of all of the connections and all of the connection properties. Source port, destination port, inside local, inside global, outside local, outside global. And by maintaining a list of all of those details, each connection entry in the database is unique. Right? Think about it for a second. If he goes to Cisco.com and happens to hit a server that is the same as the one you go to. You go to Cisco.com, he goes to Cisco.com, right? Now, from the Cisco server's perspective, you look like the same host. You have the same IP address. So Cisco's going to respond to that address. But at the router, we've maintained a database, and that database has your port numbers. Destination port's probably the same, but your source port's probably unique. But also, I've also maintained a list of your inside local addresses. So I know when this person responds that it goes to you or it goes to you. I'll point that out a little bit more when we get into the actual visuals here for this particular component. Yes, sir?
In other words, you can say it's like a company like Facebook. All the workers on the Facebook.com, that means all of them sharing, not sharing, but using the same public IP.
Yes.
Is that
there is a limit. There is a limit, but we'll talk about that in a little bit. But yes, I mean, that's how almost all companies work. I can't think of an instance, and I've installed a lot of networks in my time, an instance where that was not the case. Where outside of static translations where we didn't use PAT. It's what people use. Okay? So what is the difference between NAT and PAT? Well, NAT, we know, well, it depends on what type. If we're using static NAT, it's a one-to-one translation. If we use a pool, every host that goes out grabs a different address from the pool. The problem is that pool has to be large enough to support all the hosts. Whereas PAT, everybody gets translated to the same address. Okay?
Or, like, because you mentioned before that ideally you want to set up statically for the server.
Yeah, oh, well, I mentioned you want to, I'm going to say, sorry to interrupt, I just want to make sure people online here. I mentioned that we want to set up addresses statically for a server, but only if people need to access it from the internet. So go ahead and continue with your question.
Okay, can you do like, can you set it up like for it to use PAT, like just specifically?
No. You can do port forwarding. Port forwarding is not PAT though.
Okay.
Port forwarding is more of a policy-based NAT, right? Where you putting kind of you're basically putting a static entry into your table based on port numbers. Okay. PAT is a dynamic process.
Okay, but can you, let's say like on an interface, can you like, let's say you have all your hosts being translating using that, and you want like a specific server to be able to use, to be translated to one specific address, and then wants to be translated to your second address?
That would be static NAT, right?
Oh, okay.
So you want everybody on the inside to be able to go out using one address, but you want your server to be always using a different address, right?
Yeah.
So you would have multiple policies. I guess that's what you're getting at.
Yeah.
You don't have to, you can mix and match different types of NAT on a device. You don't have to just use dynamic or just use PAT or just use static.
So you use that and dynamic.
Yes.
Okay.
You can use all three, right? Because when you see the configuration, you'll know what I mean by that, because you define policies that allow you to identify who's getting NAT into what.
Oh, okay.
Okay. We have a question on here. What if we consume all the ports available? That's a very, very important question. That is actually something I'm going to discuss in a little bit, because that can happen. Think about it. We haven't seen layer 4 yet, but within layer 4, the port field in TCP and UDP is only 16 bits, which means we only have 65,536 ports. It is highly likely in a large organization that you could use up all those ports. All right? So yes, in that case, we would use something different. Dynamic NAT with overload. It's called dynamic NAT with overload. I will defer the details of that discussion to later, because we're actually going to see that as an example when we go through the rest of our discussion here. Okay? So the last thing we'll do in this chapter here is we'll kind of go through some configuration examples. And if you guys have any additional questions as we go through the examples, feel free to ask them. All right? The first one, of course, we talked about was static NAT. So let's talk about how to configure static NAT. There are two tasks that you essentially will do. Number one, you'll create a mapping of interfaces, right? You'll create this mapping of interfaces. Well, I actually said that was step one. That's the second one listed there. In other words, you're going to define which interfaces are participating in NAT. Specifically, which inside interfaces are participating in NAT and which outside interfaces are participating in NAT. Secondly, which is the first bullet point here, you're going to define your policy. And the policy is essentially what is that mapping from inside local to inside global. In other words, what is the address mapping between private and public? All right? It's actually not that complex, especially in a Cisco router. It's a little bit more complex than a firewall. Not much, but a little bit more. All right? In fact, this is the entire configuration. Basically, 3 lines of configuration. Again, this is a Cisco router. It would be different if it was a firewall. Concept is still the same. The first line that you see here is my NAT policy. That is my NAT policy. And by the way, you can have multiple NAT policies. It's not just a single policy. You can have lots and lots of policies. Incidentally, if you guys are interested in playing with these configurations, there's nothing stopping you from building this in Packet Tracer and doing the configuration yourself. We don't have time to do that today, but you could certainly go back to this slide, or if you're watching this video online, you can pause the slide and throw this network together real quick in Packet Tracer and do the configuration. What does my policy say? I'm going to do translations inside, meaning the traffic from the inside is going to get translated. The type of NAT that I'm using is static NAT. The type of NAT that I'm using is static NAT. Source static means I'm using static NAT. Here is my inside local address. Here is my inside global address. So 192.168.10.254 is going to be translated to 209.165.201.5. Make sense?
Yeah, so the inside comes first, the inside local first, and then the inside global.
Correct. In a Cisco iOS router, right? Again, configurations might be slightly different on other types of devices. So the first address is my inside local address, or what we call the real address. The second address is my inside global, what we call the translated address. Very important to understand, though, implementing the policy does not actually make NAT work. The second thing you have to do is you have to tell the router which interfaces are participating in NAT. My gigabit Ethernet 00 interface, which is the one on the left, that is the inside of my network, and the serial 010 interface is the outside of my network. By typing in IPNAT inside and IPNAT outside, we are establishing how the translation occurs. When traffic comes from this web server to this interface, because I have IPNAT inside, I check my policy. If the policy matches the host, I do the translation and I create an entry in my table. By traffic coming into serial 010, I have IPNAT outside. That instructs the router to look at the table to see if there are any active translations for that particular traffic flow. Yes, sir.
Out of curiosity, for the inside, can you map that to a virtual interface?
You can map it to any type of interface. Could be a loopback, although you would never really have traffic generated from a loopback. It could be a sub-interface. It could be anything.
All right.
Okay. On a switch, on a multi-layer switch, it could be an SCI. All right. Why would you input the policy before selecting the router interfaces? Does it matter? It doesn't matter, actually. It doesn't matter. It's kind of like, well, I want to relate this to something that you guys have already seen. Well, I can't really. It's kind of like when you're doing an access list. You can, well, actually, it's kind of like port security. Whether you decide to implement the properties of port security first and then turn it on, or whether you decide to turn it on first and then implement the properties, it doesn't really matter, right? But both of them have to be done for it to be effective. By the way, what happens if this host is not 254, but it's 253? And that traffic goes to the interface. The interface has IPNAT inside, right? But the packet doesn't match my policy. What does the router do with that traffic?
Drop
It does not drop it. It routes it normally. It routes it normally without translating it. Remember, routers don't route based on source. Routers route based on destination. So actually, that packet is probably routable. Now, does that mean it's going to come back? No, because we're using a private address to go out to the internet. But I want to make it clear that just because a packet doesn't match your policy doesn't mean the router stops routing. It just doesn't translate. Does that make sense? Let's see, we have another question online. Is there only an inside and outside designation? Nope, that's it. I mean, yes, that is true. There's only an inside and outside designation. Don't confuse inside and outside with the concept of a firewall where you have inside, outside, DMZ, and so on. All right? On a router, we simply identify inside as our real addresses or our private addresses, outside is our publicly facing interface. Can you have more than one inside or outside? Absolutely. You can have multiple insides and outsides. I might have another interface, I might have another interface that goes to the internet here, and I can make that outside as well. And then I also might have other interfaces on the router here that I want inside.
Can we have one outside and multiple, and take it to the multiple inside?
Of course.
And
Absolutely.
vice versa?
Yes, absolutely. Multiple outsides to one inside. You have to understand something, guys. Routing is separate from NAT, okay? If for some reason my router has a route in it that points to X over on this internet connection, and then it has another route over here that points to Y, both of these interfaces could be outside. I could only have one inside, but I could have multiple policies. And I could say, okay, here's my first policy right here, and it so happens that 209.165 is X, which means that after NAT takes place, the traffic gets routed to X. But maybe the other network is 208, and that's Y. So after NAT takes place, that traffic gets routed to Y. Routing happens after NAT. Routing is done separately from the translation. All right? So how does static NAT work? Well, we've kind of already done this. And I'll answer your question here in a second, Jamie. But we've got a web server and a client. Now, the flow of traffic in this is in this direction in this case, because this is static NAT. So we've got a client on the internet that is going to, it's coming from this address, 209.165.200.254, and it's trying to reach this address, 209.165.201.5. And 201.5 happens to be translated to 10.254. This is my outside interface. This is my inside interface. All right? So when the traffic hits this interface, the router looks at its table and says, oh, okay, you're trying to get to this address. We have an entry that translates it to this address. So the translation takes place. The traffic goes to the inside host. The inside host responds. It responds to the 254 address, which is kind of irrelevant, actually. It goes to the router. Because that router has an inside NAT policy applied, we check the policy, not the table. We check the policy states to translate, and then we send the traffic out. Okay? Jamie says, how does the firewall affect NAT? Usually the firewall is doing that. Usually the firewall is the device that's at the edge of our network, and it's actually the device that's performing NAT. However, if it's not, if you're doing NAT prior to the firewall, which does happen from time to time, it doesn't matter. Packets are packets. Whether they're, as long as they're routable, as long as the device knows how to send the packet, and a firewall is essentially a router, it has much higher level functions. It goes all the way up to the application layer. But from the perspective of switching data, it's a router. It's not a switch. So it just looks at, it has a routing table or default route. It looks at that and does the routing.
So that can be done on a router and a firewall, or either or.
Absolutely.
Yeah.
Yeah, absolutely. All right. So I'll go through the steps one more time. It's very simple. Number one, you've got a client on the internet. Oops, sorry about that. You've got a client on the internet that wants to reach your web server. You publish either through DNS or you give them a static IP or the actual IP. You publish this address to the people on the internet. Okay? What's going to happen? that traffic is routed to this router by the service provider or whoever owns that particular network. Because I have outside, IPNAT outside on the interface, that instructs the router to check our database to make sure that there's a translation rule in place. If there's not a translation rule in place, that traffic gets denied at that point. All right? There is a translation rule in place, so we translate to the inside local address. That traffic goes to the host. The host responds to the 254 host, comes back to the router. Because we have a policy applied to that interface, the translation takes place again, and it gets routed out to our destination. All right? Keep in mind, as complicated as it seems, it really isn't. You specify your inside and outside interface, and you specify your NAT policy, period. Okay? How do we verify NAT on a router? Well, there's a couple of different ways. There's actually really two commands that we use predominantly. Show IP NAT statistics, all right? And I can see here I have one static NAT translation, or one static NAT entry. The outside interface is serial 010. The inside interface is gig 00. I can see if this NAT policy has been enacted. In other words, is it being used? So far, no. But notice once I start to establish a connection to a web server, we see hits in the translation.
So when it says hit 0, that means that the NAT is established, but it's not active.
Well, static NATs are permanent, so they're always established, right? If we see 0 hits, it just means it's not being used.
Oh,
correct.
Being used.
It doesn't mean it's not active. You know, hits are just the number of times that the translation has been used. If you want to see NAT taking place, you would have to do a debug IPNAT if you wanted to see the actual translations taking place. We'll see an example output of a debug in a little bit. Okay. Dynamic NAT. Like I said, the least common form of NAT, but it is used often in large enterprises in combination with another type of NAT. Okay? What do? We set up a pool of public IP addresses. That is called our inside global address pool. Now you know what inside global means. The public IP representing the inside hosts. All right? There's a mistake there. Hold on one second. Discard that. The static NAT, not dynamic NAT. All right. With static NAT, we have a single address translated to a single outside address. Actually, you know what? That was correct. I'm going to explain why it was correct here in a second. It is dynamic. Actually, static and dynamic kind of do the same thing. What they mean to say with this, dang it, what they mean to say with this is they're saying that when you want to go to the internet, you grab an address from the pool. But you're the only one using that address. Does that make sense?
Only one person.
You're the only one using that address. Now, the number of people that can go to the internet depends on how many addresses are in the pool. Does that make sense? If I have 100 addresses in the pool, then 100 people can go to the internet. If I have 5 addresses in the pool, then 5 people can go to the internet. All right? Sorry about that. I was reading that and interpreting that as our static NAT definition, which is a one-to-one NAT translation, right? Where you have a single inside address, always translate it to the same outside address. But that's not actually what this is saying. It's kind of what it's saying, but not completely. Could be interpreted in different ways. All right? So how does dynamic NAT configuration look? Well, it's a little bit more complicated than static NAT. But you can see it's still not that difficult. Oops. It's still only a few commands here. Not a whole lot of commands. All right, here's the entire configuration. As you can see on the interfaces, we're still doing our NAT inside and our NAT outside. We're still identifying who gets translated. NAT inside, NAT outside, or excuse me, where the translation takes place. Not who, but where the translation takes place. Okay? In addition, we have our policy. This is my policy. Now, this is where it varies quite a bit from our static policy. We're still doing IPNAT inside. But we're now saying, okay, we're going to translate the addresses that match access list 10. Access list 10 is just above that line. In other words, if you're coming from the 192.168.10 subnet, we're going to translate you. Now, we haven't talked about access lists yet. That's another discussion that we'll have today. But, so for now, we'll just say that it means that essentially if your source address is 192.168.10.anything, you're going to get translated. And what are you going to get translated to? What are you going to get translated to? You're going to get translated to an address from this pool. And the pool is called NAT pool. By the way, highly recommend this to you guys. When you type commands into a Cisco router, regardless of whether you type those commands in uppercase or lowercase, in the running configuration output, they always show up in lowercase. Always. Unless you're naming something. If you're naming something, it will show up however you write it. So for me, whenever I'm naming something, if I'm naming an access list, or if I'm naming a NAT pool, or if I'm naming a DHCP scope, I always put those names in uppercase. Because then I can easily identify in the configuration whether it's something that is named or whether it's a command. See, if this NAT pool was in lowercase, you might think that that's syntax rather than a name. All right? Just a little hint. Kind of make your life a little bit easier when you're dealing with configurations. Of course, the NAT pool itself is defined. IPNAT, NAT pool. And what do we identify? We identify the beginning of the pool, which is 225, the end of the pool, which is 254, the subnet mask for the hosts that are getting addresses from the pool, which in this case is 224 as well, or 224, not 254. So this is the beginning of the pool, this is the end of the pool. If all of those addresses are exhausted, if all those addresses are used, then nobody else can go out to the internet. Well, they can go out, they just won't be translated, which means essentially it won't work. All right, we have a question from our online participants. What if by some sort of mistake an IPV4 address from the pool gets assigned to 2 hosts at once? That won't happen. It simply will not happen. Okay? Because when an address gets assigned, it gets put into our translation database. The router knows it's being used. And by the way, if you accidentally try to configure a static NAT policy using an address that's already defined in a pool, the router will also tell you you can't do that. It'll say, oh, you're already using this address in a pool. You can't use this for a static translation. It simply will not happen. Okay? So what is the process? Well, it's the same as any other NAT process. The difference here is that the connection has to be initiated from the inside, not from the outside. We've got a PC here that wants to go out to the interweb. They're going to try and send their traffic out. Here's our inside interface. Because we have NAT configured on that inside interface, we're going to check our policy. As long as the policy matches, in other words, it's coming from the 10 subnet, we're going to grab an address from the pool, go out to the internet. All right? The server is going to respond. Because this is my outside interface, I'm going to check my translation database to make sure that there's a translation, and then I'm going to translate that address to the inside local host. All right? I'm sorry, but I did not hear the last part about running out of an IP address in the pool. It's simple. If there aren't enough addresses in the pool, you won't get translated. It's not that you won't get routed. I want to make that very clear. Your packet will still get routed to the outside. But the problem is the source of that packet is from an RFC 1918 address. So the return traffic will never get back to you. In fact, the service provider most likely will drop that packet because they'll think that you're trying to attack somebody using a spoofed address, because private addresses are not allowed on the internet. Okay? Okay? This is a continuation of the process. In this case now we have a different host that wants to go out to the internet, and of course they're going to grab the next address in the pool. All right? The last form of NAT that we'll talk about is port address translation. But we're going to see a scenario where port address translation is combined with this type of NAT that we just talked about to give you more flexibility. The other command, we saw one command to verify NAT. This is the other command that we typically will use to verify NAT. Show IP NAT translations. And when you do a show IP NAT translations, it will show you your active translations. I'm not sure why these pieces are not filled in. They would normally be filled in. You'll notice you've got a protocol column. Protocol could be TCP or UDP or ICMP or whatever. You've got your outside local address, your outside global address. The reason why I take exception to this particular output is because dynamic NAT translations are not permanent. They don't stay in the table. They only go on the table when there's an active connection. So if there was an active connection, you would see all of the information filled out. I think there is another slide that shows the entire field filled out as it should be. You can do a clear IP NAT statistics. And again, you can do a show IP NAT statistics. In this case, we have two active dynamic translations. And you can see all the relevant information. What is the outside interface? What is the inside interface? That's not going to work. This slide is definitely messed up. I guess it could work. Serials, you can go from serial to serial. It doesn't matter. I looked at that and I thought, well, those are the same interface numbers, but they're not. One is 001 and one is 010. Okay? It doesn't match our topology that we were looking at previously, but you get the idea. All right? In fact, we're pulling addresses from a pool called NAT-pool1, and the start of that pool is 226. The end of that pool is 240. We have two allocated addresses, meaning we're using 13% of our pool presently. We don't see this NAT because it's just not practical. You don't have hosts in your network anymore that don't go to the internet. It's just, well, very, very rare. Okay? Now let's talk about the third and final kind of NAT, which is port address translation, where everybody on the inside of the network gets translated to the same address going out to the internet. We've got our inside network. In fact, we actually have two inside networks. We have the 11 network and the 10 network. And then we've got some LAN connection here or whatever. We've got an outside interface with a public address. And we've got some destinations on the internet that we're trying to reach. As with all forms of NAT configuration, we have to specify which interfaces are inside and which interfaces are outside. In this case, gig 00 is our inside, which would be this interface here, and serial 010 is our outside, which is that interface there. Look at our policy. Here's my policy. I'm going to do NAT translation from the inside using access list 1. Sorry, let me do that. Access list 1 to match my inside hosts. And by the way, access list 1 is here. And that's saying anybody that has an address of 192.168. Again, we haven't gotten into access lists yet. We will in a little bit, but anything that begins with 192.168 is going to get translated. But what is it going to be translated to? It's going to be translated to the IP address on my outside interface. Now, if I took that out, that would be a bit of a problem, wouldn't it? Technically, it would work. But what would happen? How many people would be able to go to the internet? One person. And here's the key. The word overload means use that address over and over and over again. Use that address over and over and over again until it's exhausted. There is a limit, by the way, because when you're doing port address translation, you maintain a database of the connections based on port numbers. Well, there's a finite number of port numbers. If you have 100 employees, this would work out just fine. But if you have 10,000 employees, this would not work because you would quickly run out of port numbers. You have to think about it. PCs on the inside of the network aren't just going to the internet one time. They're going to the internet a lot. I'm going to Office 365. I'm going to Dropbox. I'm going to OneDrive. I'm going to WebEx. Every single one of those connections is a separate and unique connection. And they have to have unique port numbers. All right? So we had a question earlier about, well, what happens if I run out of ports? What do I do? Well, you actually have an option to overload a pool. You can create a pool of addresses, whether it's 1 address, 2 addresses, 5 addresses, 10 addresses. And instead of overloading the interface, you overload the pool. What does that mean? That means that when you go out to the internet, whoever goes out to the internet grabs an address from the pool, and that information gets tracked. They go out to the internet. The next person that goes out to the internet grabs the same address from the pool. But we identify the difference between those connections with the port numbers. Until that address is exhausted, then we use the next address in the pool. Does that make sense? So now instead of having 60,000 possible connections, a little bit less than that, instead of having 60,000 connections, you have 60,000 possible connections per address in the pool. All right? But how does the router keep track of these connections? Well, here's how. You've got PC1. PC1 wants to go out to the internet. Specifically, PC1 wants to go to 201.1. The source address, the inside local address is that. The source port is that. Source ports are random. The PC generates its own source port whenever it opens up a connection. We'll talk more about that when we get into the transport layer. But PC1 happened to pick 1444. The inside global address, or excuse me, outside local address is 209.165.201.1. The destination port is 80. Of course, inside local gets translated to inside global. Make sense? And that information goes into the database. It's pretty specific information if you look at it. You've got a unique internal address, colon, port number, inside global, which is a translated address, colon, port number, outside global, colon 80, which is the port number, and so on. Now, it's extremely rare, but if another PC wants to go out to the internet, they may or may not choose to use the same port because those PCs don't communicate to each other. They don't identify who's using what port, and those ports are randomly chosen. If that occurs, in addition to translating the host, we'll translate that port from 1444 to 1445. If 1445 is already used, then we'll use 1446 or 1447 or whatever. What's the bottom line here? The bottom line is that every single entry in this database is unique. Every single entry in that database is unique. So when the traffic comes back to the router, it's very easy for the router to identify which host I'm translating to because of the characteristics of that traffic flow. Now, I couldn't base it on this, right? Because that's putting the cart before the horse. The translation has to occur. Now, if these two guys had the same port number, that'd be a problem, wouldn't it? That might be. In this particular case, we can uniquely identify these connections based on the host that they were talking to. But if they were happen to be talking to the same host, that would be a problem. So as long as these ports are different, hence the term port address translation, as long as those ports are different, the router has no problem identifying who to translate that traffic to. This translation database can be very, very large. You can imagine it can have tens of thousands of entries, right? Especially if you have lots and lots of clients going to the internet. So on the reverse side, of course, the host responds. We hit our outside interface, we check our database, and we match the entry, and we do the translation to the receiving host. Okay? Show IP NAT translations. This is the table that I was referring to. This is a fully populated table. You have the protocol. Inside global means the public address, and then those are the port numbers. In this case, you'll notice that we didn't have to translate the port numbers. Why? Because the port numbers were already completely different. Inside local. Notice we didn't do any translations of port numbers. 42558 stayed 42558, 51839 stayed 51839. As long as the ports are unique, we don't have to worry about translating those ports. So you can see from this table that the router maintains this list, and by maintaining all of these details, by putting all of this flow information into the table, I can easily identify what traffic goes to which host. This is what's happening at your home router. This is what's happening at the hotel router. This is what's happening at your company router. Go test it. If you want to see if this is the kind of NAT you're using, go to one computer in your network and go to ipchicken.com and then go to a different computer in the network and go to ipchicken.com, and you will see that most likely it's going to be the same outside address. Okay, same inside global address, I should say. All right, now be very careful with this command, clear IP NAT translation star. When you do a clear IP NAT translation star, you may get some TCP drops because the return traffic won't match any of the entries. Now those translations get rebuilt very quickly, so you might not notice the difference, but it is possible. Okay? All right. You can also do a debug. Now, we haven't talked about debugs in this class so far, but there is a big difference between a debug and a show command. Show commands give you a snapshot in time. In other words, show IP route. Okay, as soon as I execute that command, I see my routing table at that time. If I leave that on the screen for a half an hour, it's possible that that information is not the same as what I actually have. Debug commands give you the information in real time. You have to be very careful with debugs because they do require a lot of resources. All right? In fact, a lot of debugs will actually crash a router or a switch if you run them. Cisco has a debug option called debug all. Some reason they've decided to add that to their repertoire. Debug all means turn every possible debugging option on. You type that command, and I guarantee no matter how busy that router is or how busy that switch is, it will not respond anymore. It will crash because you're debugging every possible debug. All right? Be very careful with debugs. We're actually going to do a debug with RIP a little bit later on. Debug IP NAT. So what I'm telling the router to do is show me in real time when translations are taking place. And I can see there are essentially two separate transactions happening here. You see the 2817, 2818, 2819, 2820. That's one set of transactions. And then you got 4180, 4181, 4182, 4183. That's another set of transactions that are taking place. S stands for the source address. 10.10 is being translated to 200.226. The destination is 201.1. The other transaction is the return traffic. The source is 201.1, and we're doing an untranslate, or we're translating back to the inside local address from 200.226 to 10.10. By the way, if you want to turn off debugs, U space ALL. Undebug all. Undebug all. You can also do a no debug IP NAT. You can do a no debug IP NAT, but if you don't know what debugs are running and you want to just turn them all off, just type U space ALL, undebug all. Okay? You can also do a show debug if you want to see a list of all the debugs that are running. Show debug. All right? So that concludes our discussion about NAT. Hopefully you have a bit of a better understanding about NAT and how NAT functions. As always, we'll be uploading this video to our YouTube channel hopefully later today. All right? All right, stop recording. And we're going to take a quick break, and then we're going to get into the next chapter.